All right, so let's move into some strategies for solving related rate problems. You'll see in front of you 6 steps. If you're in my class, I'll go ahead and link to a PDF in Google Classroom. If not, you might want to take a screenshot of this and file it away because this will be a useful reference. And what I'm planning on doing here is I'm going to just walk through step by step in a variety of problems. The easiest way to explain these related rate problems is to just show you example after example. So this video will have one example. Very quickly, step number one, understanding the problem, identifying variables. Notice variables whose rate of change you seek versus rate of change you know. Mathematical modeling, I recommend drawing a picture for every single one of these, distinguish constants from variables. Equation, write an equation relating the seek versus know variables. Differentiate, and remember this is going to be implicitly because it's with respect to time. Finally, substitute values for quantities that depend on time. This is really important that you do this step at the appropriate time. If you do it too soon, what it does is it freezes your picture in place. Something changing at a rate of 6, you put in 6, you've said, aha, we're only dealing with what happens when that rate of change is 6, because then the derivative of that becomes 0. And then finally, interpret the solution. It's going to be important to remember that every problem that we're doing here, the solution means something in the context of the problem. So let's take a look. We have a hot air balloon that is rising. It is rising at 0.14 radians per minute. So let's just go ahead and jot down what we know. So step one, we're going to identify, we have the rate of change of the height of, or the angle of elevation of this hot air balloon, and I'll draw a picture in just a second, is 0.14 radians per second. And again, the question says that a hot air balloon is rising and you're measuring the angle of elevation. At an angle of pi over 4, how fast is the balloon rising? So that's our dH dt. And we know that the rangefinder is 500 feet from the base of the the base of the balloon. So in other words, directly under the balloon. So let me draw a quick diagram. Without reference to the problem, it probably would have been easier to have drawn the diagram first, but I'm trying to follow these in order. Here's my diagram. Here's my balloon. I've got my rangefinder 500 feet away. The balloon is at some height h. Here we'll add a little basket. Be artistic. It's okay to be artistic during math. And the rangefinder is, we'll pretend that's an actual right triangle with straight sides. The rangefinder is at some angle, and the angle is changing as the balloon rises, and the height is changing as the balloon rises. So important that we not label this theta equals pi over 4, that we not insert this number into the equation because it's changing. And remember, we don't want to put in numbers that are changing until the very end. And of course, we don't know this, so this is what we're trying to find, is that right there. So we need a relationship between angle and height. Fortunately, we remember that the tangent of the angle is equal to the height divided by the base, the opposite over adjacent sides of the problem. And we can now differentiate this. We have a relationship between, and this is step 3, a relationship between the variables that are changing. Taking the derivative, we find that secant squared theta d theta dt, notice that d theta dt is very, very important, is equal to 1/500th times dh dt. We now know everything except for the thing we're looking for. We know the angle, we know the rate of change of the angle, and of course 1/500th is a constant. So we can substitute. Remember, step 5 is substitute, and we get secant squared of pi over 4 times 0.14 is equal to 1/500th the quantity dH/dt, which is what we want. And doing a little bit of typing into our calculator, we discover that the rate of change of height with respect to time is 140 feet per second. Units, very important because they give you a frame of reference for your answer. And finally, 6, what does the interpretation look like when the angle of elevation is pi over 4 radians? The balloon is rising at 140 feet per second. Everything in there is important. It is not enough to just say 140 feet per second. What about 140 feet per second? Oh, the balloon is rising at 140 feet per second. Always? No. Just when the angle of elevation is pi over 4 radians. All right. If you are in my class, go ahead and jump to your book and do exercise 11. I will post up a PDF of the solution. And if not, hope this helped. Hope you learned something. Have a great day.